Hello everyone, I'm Haofeng Li. I'm assistant professor at the Institute of Computing Technology of Chinese Academy of Sciences. Today I'm happy to present my work, which is model-aware context-sensitive pointer analysis. And this is joint work with Chenghao Shijie, Lu Lianli, and Zuxuan Zhao. Pointer analysis statically computes the abstract locations of pointer variables in a program. Pointer analysis provides a foundation for various applications, including code-graph construction, bug detection, compiler optimization, security analysis, taint analysis, and others. Several famous analysis and compilation frameworks, such as Vala Suite, IVM, Dup, Tile, Qilin, and so on, have implemented pointer analysis. To get all points to sets, the pointer analysis solver iteratively applies rules specific to each kind of statement to every statement until reaching a fixed point. Pointer analysis has two primary goals. First, analyzing as many reachable methods as possible. Second, achieving high precision with as small cost as possible. So how can we achieve the two objectives? Two is software development and maintenance. The concept of model system has gained popularity, such as the Java Platform Model System, shorted by JPMS. The model system provides stronger encapsulation for code, which is critical semantic information for pointer analysis. To define a model, JPMS introduces some principal directives. A provides model directive specifies that a model provides a service implementation. A uses model directive specifies a service used by this model. This scheme is also called SPI. For example, model M1 uses animal interface. Model M2 provides implementations dog and cat. Without modeling SPI, we will missing some points to relations. A points to the object dog and object cat. A required model directive specifies that this model depends on another model. For example, model A requires model B, but not requires model C. This means model A can access class B from model B, but cannot access class C from model C. An export model directive specifies one of the model's packages whose public types should be accessible to code in other models. For example, Model B exports package test, but not exports package test2. So Model A can only access the class B in package test. Unfortunately, existing pointer analyses are unaware of the model system mentioned above. We propose to model the semantics of directives provides and uses in JPMS to recover missing points to relations. We design a model-aware context-sensitive analysis which can propagate and apply critical context by exporting semantics of the directives requires and exports to balance precision and efficiency better. For completeness, to model the provides and uses directives, we separate it into three parts. First, service loading, where services are loaded and bound to tagged objects. Second, propagating service along transfer function. Third, retrieving the implementations of service, instantiating corresponding objects, and recovering missing points to relations. There is a rich works optimizing the efficiency and the precision of point analysis. One of the key technology to improve precision is context sensitivity. In context-sensitive analysis, both point variable and abstract locations are qualified with context, effectively distinguishing their different dynamic instances. There are three mainstream variants of context sensitivity: cosine sensitivity, object sensitivity, and type sensitivity. In general, a context is represented by a sequence of key context elements. For cosine sensitivity, the context elements are cosines, such as line 4 is the context of function 4 in our example. For object sensitivity, the context elements are allocation sites of receiver objects, such as allocation site O in our example. For type sensitivity, the context elements are types of receiver objects, or the type of the Decorator class, such as type A or type B in our example. As the depth of context increasing, the results will be more precise. On the contrary, the time and memory overhead will grow exponentially. So how to balance precision and efficiency better? There are two primary challenges. First, is there more effective representation of the context? Second, how to propagate context elements within a model. In the following slides, I will introduce our approach. For change 1, our findings reveal that the receiver object of a method invoked in another model is a critical context element. So we use such objects as context. We call such objects the model frontier. The model frontier can help us select critical context when solving context-sensitive point analysis. However, when processing the code within a model, the information of the model frontier will be missed. So we need to propagate the model frontier into the internal code of a model. The OAG is used to describe the relationship of object allocation. A path in an OAG is exactly matched with the context of a method. Based on OAG, we define the MDG. The MDG is built by annotating the OAG with model depth, which means the shortest path length from model frontiers to the current node. We use the depth to limit the propagation depth of the model frontier contexts. However, previous work relies on a pre-analysis, which is considerably slower to calculate OAG. To improve the overall performance, we design on-the-fly algorithms to build both OAG and MDG. Here are the rules of our model where context-sensitive point analysis. The details are in the paper. Here are the experiment settings. We evaluate MPA on Da Capo benchmarks and 7 popular programs such as Ant, ANTL4, Checkstyles, Gibos, and so on. To evaluate the impact of our research, we focus on the 3 research questions. Excluding programs developed on early versions of the JDK that didn't utilize the SPI scheme, we use the remaining programs to evaluate the ability to find more reachable methods. For Lombok benchmark, only 16 application methods are analyzed without module SPI. while 1,455 methods are discovered after modding SPI. For other programs and metrics, modding SPI can always improve completeness. MPA is nearly as fast as context insensitivity for most benchmarks, while its precision is superior to that of one object sensitive on average. MPA can also compile with selective context sensitivity to further balance precision and efficiency. Here is the partial results. More details are in the paper. Previous OAG construction depends on a pre-analysis, such as context-insensitive analysis. However, the percentage of the time of our on-the-fly MDG against the time for context insensitivity ranges from 2.4% to 14.3%, with an average of 7.8%, compared to the previous approach, which used a context-insensitive pre-analysis. Our on-the-fly approach is more effective.